I'm Piper. I've given this talk. I've given this talk about 4 different times, 4 different formats. That's interesting work, but not what I'm here to talk about. My Twitter handle is PA Thunstrom. You can find me pretty much anywhere with that, including GitHub, where you can find the slides and the code sample I'm going to show later. So, obviously, I'm talking about Pygame. In general, I like to talk about why I like Pygame, which actually the truth is I'm kind of getting tired of it. There's a lot of limitations as you get better with it. But games provide a lot of interesting challenges. There's a lot of questions you have to answer and figure out on your own, especially when you're working with something like Pygame that isn't quite a framework like Kivy or Piglet, who give you a lot of tools straight off the bat. This gives you a lot of low-level things, and you have to figure out how to put them together. Plus, it's just fun making games. If you look at my GitHub repositories, that's most of them, is various games of disrepair in various states of disrepair. So, things I want to talk about. The best parts of Pygame. Basically, the pieces you're going to want to start making your own games. I've skipped a lot of the things I normally talk about when I do this talk, mostly because there's a lot of things I've never used. The CD-ROM module. I literally never used it in 2.5 years. I don't talk about the sound module. The mixer is fairly simple. You just load a file and tell it to play. So we're going to skip that one. Obviously, I'm going to show you how to put them together, and I will discuss a little bit some different design patterns that I've picked up from building different games. There's a couple of ways you can build things in Python. Popular things are like the singleton pattern, which Python you kind of frowned on making singleton classes, but there's ways to do it. As I said, what I'm not talking about, artificial intelligence I'm not covering. You guys can figure out how to make computer-controlled things do what they do. Installation issues, I talk about this a lot. This package is insanely difficult to install on some systems. If you're on Ubuntu, it's nice and easy. You can apt-get it, python-pygame. Mac, there is a precompiled binary, doesn't always work. Windows, you got a 50-50 chance of it doing what it's supposed to do. So good luck. Though the good news is the precompiled binaries for Windows, there is one that works specifically with Python 3. So if that's what you code in, that's going to be your easiest way to get that. As I said, there's a bunch of packages. I've never used them. Some of them, I'm not even sure what they're supposed to do. And there's actually one that I'm not even sure where it is. In the documentation, there is a math module. In the source code, it's there. None of the precompiled binaries seem to have it. So if you need vectors, you're going to have to write your own. Sorry. And so let's get to the pieces. Starting with the surface class. The Pygame surface is essentially just a pixel array. There's actually a pixel array that gives you direct access to the pixels in the surface. But what it really is a digital canvas. You can draw on it. You can take one and paint it onto another, things like that. There's also a special one that represents the actual screen or window. These are the major ways you can get a surface. Obviously, you can just initialize one. In this case, this is just creating a surface that's 300 by 300 pixels. That's all it does. Image.load, you hand it a PNG or a GIF, or I think JPEGs. There's a handful of image classes that it can take. It will create a surface the size of the image you load. And then the important one is this one. Pygame display.setMode is actually going to be the one that gives you that special surface. That is your monitor. So the mode is, again, pixel, it's your resolution. I have not found a good way to systematically discover what your system resolution is using Pygame and similar modules. So usually you need to know ahead of time what size you're targeting. Like I said, display represents the screen. Really simple. So anything that you draw to the display when you call update on pygame.display will show up on your monitor. So things you can do to a surface. So convert. This is actually important for that primary screen. Any other surface you plan on blitting to the actual hardware screen, you're gonna want to convert. It speeds up a couple of cycles when it blits. What it is if the pixel formats don't match, it's going to convert each other surface every time you blit it. If you convert it ahead of time, then it doesn't have to do that. Blitting. Take one surface, paint it onto another surface. In this case, the surface that you're calling blit on is the one that you're painting to. The one that you pass in is the one you're painting from. The XY is going to be what the top left corner of the source pixel of the source surface. And the origin is the top left. I don't know if anyone's done graphics processing. It's pretty standard. I know Kiwi and Piglet both go from the bottom left, like you learn Cartesian plane. Most other graphics hardware goes from the top left as your origin. Transparencies. So obviously, you're going to want some transparencies since everything's a square usually. Not all sprites are perfect squares. Color key, when it works, I actually had a bug this weekend making the demo that color key wasn't working. Color key, any pixel that is the value you pass in becomes a transparent pixel. Or you can set the alpha value on the whole surface. So if you want a 50% transparent object, you just set alpha to 124 something. It's 0 to 255, so that's, in fact, that's your Pygame color object is a 3-tuple RGB 0 to 255. Same idea. Fill. This one's really easy. Fill the entire surface with one color. Next thing you can do is start using the draw module. You can draw various things, starting with lines. I'm only going to cover 3 of them, but there's about a dozen different drawing functions. But they all follow some pretty standard models. So the line, you just pass in the surface, the color, a start point and an end point. Start point and end points are, of course, an XY tuple. And then a width if you're drawing a line, or if you're using an AA line, it's going to be a single pixel line, and then you can blend or not blend, which determines, it'll either paint the true color or it'll blend the color you're wanting to draw with the color underneath it. So that's what blend does on the AA line and AA lines. Draw lines, you pass in a list of points, and it'll draw a line from each point to each point. If it's closed, it will, the first and the last one will get drawn together. And then polygon is essentially the same thing, but always closed. And again, these all pretty much have the same signature, which is why they're all bunched here. Circles, surface, color, position, which is the center point, and the radius. And then width is obviously the width of the outer line. If it's 0, it draws a filled circle, which actually has a couple of bugs because of the way they draw it. And again, points are almost always XY tuples. Rectangles. So with a rectangle, again, you give it the surface you're drawing to, the color. You pass it a rect object, which I'll discuss in a moment, and again, a width. So with this, ellipse and arc both share a similar signature to this. An ellipse, you do the same thing, except it'll draw an oval that is bounded by the rect. And then arc, you have to pass in the beginning and end angles. I don't use that one much. It's probably one of the least useful draw functions. So, covering a rect. So rects are actually one of the really nice things in this package because they're axis line bounding boxes, which are really simple to implement yourself, except they put a lot of good attributes onto them to make it really easy to use them. So making a rect, there's basically two different signatures. These are essentially the equivalent. You give an X, a Y, a width, and a height. So it's defined the top left corner, the width, the height. You can pass it in as two tuples as well. And like I said, they're just rectangles. They're axis-aligned bounding boxes. But this is really part of the reason you want to use them. Even though underneath they're still defined by that top left corner width and height, you can assign to the center, and it will move this entire rectangle to where you want it. You don't have to worry about measuring for the center. So if you want to operate on the center of an object or the left, the right, top, there's also a mid-top, mid-bottom, mid-right, and mid-left that I didn't cover here. But instead of getting the single value for the value of the side, you get the two. You get the actual point that is the center point. Example of how it would look in code. So you just call the center and equal it to whatever you want. So this is the other fun part. Rectangles have collision methods. You can collide with a point, another rectangle. You can give it a list of rectangles, or you can give it a dictionary of rectangles. And they will tell you, with list and dict, it will give you whatever the first one that matches as a collision. If you do collide dict all or collide list all, you get a list of everything in the, you either get a list or a dictionary back of every one that collides. So this is just the bare object rectangle, which is quite useful. Now that you know surfaces and you know rectangles, we can understand sprites. So a sprite is three things. Sprite.image, which is a surface. Sprite.rect, which is obviously a rectangle. And then an update function. Anything else you want to put into your sprite classes is completely optional, and you will be putting a lot into these if you're building them because, well, that's where you keep all your game state. The next thing you need to know for sprites is sprite groups. So a sprite group is essentially just a list in most of the implementations they provide, which just holds sprites. You can add a sprite with .add. You could remove a sprite. The group.update is actually just a function that calls the update function of every sprite in the group. So this is why you've got that pattern on the previous page that showed you the sprite.update with args and quargs. Whatever you pass to update gets passed down to the next ones. You cannot get any return values, so that's the thing you have to worry about when you're designing your sprites. And then finally, group.draw. You pass in a surface. It uses the image file, the surfaces of each sprite, blitted to the rectangle as its position. If that makes sense. So wherever the rectangle is in relation to the display, that's where the image is going to get blitted. And I'll show you how that's going to work in a little bit. I'm going to cover events very quickly. These are your primary, actually these are all of the events. The ones you're going to listen for most often is the quit event. Basically every single game needs the quit event because you can't exit the GUI if you don't have it. Key down and key up for keyboard, mouse, and joystick. It's key down, key up for keyboard, mouse key down, mouse key up, and joy key down, joy key up. Mouse motion, joy axis motion, video resize, which actually I did not realize was in here and I want to play with, but I haven't got an example for you today. And then user event is the lowest value you can give any event that you want to create, which you will kind of see that in a bit. So this is the general how you handle events in Pygame. You can also do a publisher-subscriber model, which basically does this for event in Pygame.events. You just call the publish on your publisher, and it works. And then this bottom part here, Pygame event.post. This is actually an example of something I've done because game loops can get fairly deep as you're building them. And if you hit a quit event, specifically if you hit the red X on your GUI, you need the quit event to bubble up through all of the loops to close them all down. So that's why you've got this, where it's going to post the event, and then there should be another line here that actually ends the current loop. Keyboard, this is if you're not using the events, this is how you just get the keyboard. When you hit get pressed, the current state of the keyboard is passed to you as a dictionary. To get a hold of those, pygame.locals includes a bunch of k_dash key name. So k_w gets you the W key. So it's just a dictionary. You access it, it's going to be a 0 or 1. If it's a 0, it's unpressed. 1, it's pressed. Mouse, same idea, but this one's there's get position, which is the current pixel position of the cursor. There's also a get pressed and other similar things for your mouse. Mice are a little weirder to work with because the mouse buttons are mapped differently based on the hardware, not on the, it's not internal like the keyboard is. So if you have a 7-button mouse, you're going to have to experiment with what is key 1, key 2, key 3. Usually it's key 1 is your left click, key 2 is your right click, key 3 is center, and then everything else is wild. Time and clock, I'm only showing this basic thing because you're probably always going to run clock, especially once you start doing actual simulations instead of update-based games. Initiate a clock, just pygame.time.clock, and then every time you call clock.tick, you're going to get a millisecond value back. In this case, if you have a certain frame rate you're targeting, FPS is going to be that frame rate. And then we're going to show you how all of this works together. Let's see, how much can we see? So there's a lot going on here. This is a full demo that you'll be able to look at. It's in the GitHub. We're going to start over here with our sprites. So this is a player sprite. And as you can see, I left the code for setting the color key there. So as you can see, I've got an image, I've got a rect, and I have an update function. That's the minimal sprite. The rest of this is basically game logic. I generally use the self.x, self.y instead of the rectangle to determine actual location of my simulation, mostly because rects can only do integer-based, whereas if you're keeping it in a separate value, you can work with floats, which gives you a little bit more accuracy when you're doing time-based updates. Facing and velocity are just vectors. Thruster here is I'm actually setting a key value. So as you can see, this is the k-w I was mentioning before. I imported that up above. Import k-w just because I need the key value for the w, because that's what I was going to use as a thruster key. But this is actually made that if I decide to change it, I can pass in a different key value. Things you do to make it so that things are customizable later. Acceleration is just the acceleration, how fast you can accelerate your ship. And screen is actually, it's badly named, this is my fault. The screen in this case is actually the rectangle that represents the screen and not the display itself. Oh, and I forgot to show this. If you see self.rect is self.image.getRect. Any surface has a getRect attribute. It returns a rectangle or a rect that is equivalent to the size of the surface that you're getting back. So as you can see, I have a bunch of game state things up here. Some of them I can probably remove as I figure out better ways to do it, because this was kind of built on the fly. All right, so then my update function. So this is what I was talking about when I'm saying time-based updates versus cycle-based. I'm passing in a time value, which I will show in the main loop is seconds. Remember I said the clock returns milliseconds, I just divide it by 1,000 and pass it into this. We move with self.x, self.y, we're actually doing self.x plus whatever the current velocity is times time. I check rotation with this mouse.get position, get the vector that is from the center point to the mouse, rotate the hold on, facing length. Oh yeah, so I get the new facing, rotate the image based on the facing. Yes, I realize this is a lot of code to do a little bit, but this section is literally, as you can see, I'm using rec.bottom and screen.top. You can set these values to each other. So if you go off the screen with this, it's going to just jump you to the other side, so you keep coming in. So if anyone's played Asteroids, you know exactly what I'm talking about. And then accelerate. If the key is pressed, you accelerate in the direction you're going. And then we have a callback function here. So defFire is going to get, you pass in two things. Player shots and baddies are actually two sprite groups. One for bullets and one for the bad guys. Figure out which direction it's facing. You pass that into our bullet, which just needs where it's going to start, direction, a color. It's pretty generic. That's down here. So that's basically how you put a sprite together to do what you need it to do. And then we have our main loop. All right, so pygame.init didn't cover this, but basically there's a bunch of packages, especially the display package, that need to be initialized before you can use them. So the first thing you do in any Pygame script, initialize Pygame. On Windows, you also have to do pygame.quit at the very end. So just two things to keep in mind. We create the display. Oh, sprite.init is this package over here that I was just going through. That was me trying to fix things. Display area, we get the rectangle that is the display. We create a clock. We make a player group. We make the player shots group and the baddies group. We add a player to the player group. Group single, it's just a group, but it only holds one sprite. If you try to add a second one, it kicks the first one out. It's that simple. Also, it has a special attribute called sprite, group.sprite. It's whatever sprite is in the group. Then we create a player. We can create an enemy. More debug code that I didn't remove. So defstop is actually another callback. In this case, it's just in a closure to make the code a little bit easier for me. And then the while running is your actual game loop. First thing you do is you clock.tick. In this case, I'm letting it run at whatever speed it's going to run at, which on my Mac is about 30 frames per second. Next thing, we do for event in Pygame event.get. If it's quit, we're going to just stop the loop. If it's a mouse button down, and in this case, I don't care which mouse button it is, we're going to call that player.sprite.fire. Next section is the update calls. So those are the three sprite groups I've got. I just call update on each of them, each tick. Then display fill to reset the screen, the three draws, and then display.update at the very end. That updates the screen. And that's a full game. This runs, which I will actually demonstrate real quick, and then we can go to questions. That is not what I wanted. Don't mind me. So yeah. I didn't show the code for this little thing, but all it's doing is trying to target the player. So any questions, since I went over that all fairly quickly? Also, those don't actually loop like they're supposed to, but it works.
You know if you can use Pygame inside the IPython notebook?
I have never tried it, so I couldn't tell you.
If you wanted to package this up as a redistributable, have you had any luck with that?
I have found some libraries, and I've gotten it to mostly work. I just don't remember all of the tools I was using. It was Pygame package, I think, was the one I was trying to use, or not Pygame package, Python package. It had the downfall of you had to build it on every target system. So if you wanted to build it for Mac, you had to build it on a Mac to be able to redistribute on a Mac. So that's the only catch. And then obviously, if you just want to zip it up, it's Python. So as long as someone has Python on their system, it runs. Anything else?
When you do the rotation, does it like recalculate the bounding rectangle?
Okay, let me go back to the code for that one. So automatically, transform does not do that automatically. Let me find that code. All right, so right here is the code we're looking at. So the first thing I did was transform it, rotate it based on the facing. When it rotates, it does add some space to the image. So that's why I have to do this self.image.getRect again. Yeah, so I get the new rectangle. And then I just recenter it on self.x, self.y. So that's, yeah, that one's a little harder. And there's another reason I have to do it this way. I actually made this mistake in the past. Transform is fairly lossy. So every time you transform it, you're going to lose some pixel values, especially rotation. So if you re-rotate the same image over and over again, it's just going to slowly corrupt it. My snake game in my repositories is actually had that bug. So what I'm actually doing here is the initial player image, which was loaded up above, I just make a new copy of it. Anything else? No? Okay. So I guess I'm done.